everyone. In this video, we're going to talk about introduction about organic chemistry, specifically about hybridization and isomerism. This is our learning outcomes. Okay, so let's recall about sigma and pi bond. Actually, you have already learned about this in chapter 4 about chemical bonds, but specifically we will discuss about organic compounds. This is sigma bonds. Sigma bond formed because of the overlap of orbitals along the bond axis. Okay, so if you see here, we have hydrogen and hydrogen atom. They make overlapping orbitals between these two atomic orbitals, and form that we call as molecular molecular orbital. It is when wait a minute when the bonds formed at the axis, the bond axis. You can see here. This is the nucleus of one hydrogen with another hydrogen. Okay, so you can see that the overlap occur along the bond axis. So this is how you represent the sigma bond. Please remember that sigma bonds are single covalent bonds. Okay, so it can formed between s orbital and s orbital, or between two p orbitals, or between s with p, or between hybrid orbitals with hybrid orbitals. You can see when the atomic orbitals undergo overlapping process, you can see that these atomic orbitals will change. Yeah, you can see like this. Yeah, the shape will be changed like this. So what is sigma bonds? Sigma bonds are bonds that form along the bond axis. Okay. And what is pi bond? This is how you make the representation of pi bond. You can see that pi bonds is the overlap side by side or sideways, between two p orbitals, and the electrons will at the upper loop or at the below, or the below of the bond axis. So the pi bond formed above or below the bond axis. You can see that this is the bond axis, this is the nucleus, and the electron density at the above of the bond axis or at the below of the bond axis. So once again, what is pi bonds? Pi bonds are formed because of sideways overlap of p orbitals. Okay, only between p and p, and the electron density is the greatest in the two regions above and below the bond axis. Okay, this is the combination of atomic orbitals. If S and S, the type of bond is sigma, for example, hydrogen, S and P, sigma, P and P and on, P and P and on, that means, like this, you have to see about this, P and P. Okay, this is still at the bond axis, P and P and on, for example, in Cl2 molecule, hybrid orbital and s orbitals, such as in CS4, hybrid and hybrid, such as C and C in CS4, C double bond C in ethene, or in ethyne. Okay, and then P and P sideways, it is a pi bond. For example, in ethene, you will see that there is a one pi bond, and in ethyne, there are two pi bonds. Okay, you can read here that double covalent bonds contain one sigma and 1 pi, and triple covalent bond contain 1 sigma and 2 pi bonds. Now let's practice. This is carbon found in spearmint. How many sigma and pi bonds are present in this molecule? Okay, please pause this video and start to count. Okay, the answer is, you can see here, it is CH3. So if you open this, yeah, there are 3 sigma. Yeah, this is sigma. Once again, single covalent bond is a sigma bond. So CH3 has 3 sigma bonds, and then one more here connected to this is sigma as well. So how we calculate sigma bonds? 3, 1. Don't forget double bond is formed between 1 sigma and 1 pi. So this is 1 sigma, 1, 1, 2, 1, 1, 1, 1, 1, 1, and this is 1, this is 2, this is 1, this is 3, this is 1, this is 2. Okay, let's count it now. 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 18, 20, 21, 22. Oh, this should be 1, 1, yeah, yeah. This is just the arrow here to show that this is 1. 22, 25. Yeah, so there are 25 sigma. And how many pi bonds? Pi bond is double bond. So there are 3, right? Yeah, this is pi bond 1, 2, 3. So 20 sigma and 3 pi bond. D. Okay, this is hydrogen cyanide. Yeah. The bonding between carbon and nitrogen atom consists of 1 sigma and 2 pi bonds. Sketch the shape of a sigma bond and 1 pi bonds in space below. Show clearly the position of atomic nuclei in each diagram. Please try. Okay, sigma bonds can be represented by a diagram like this. Okay, this is 2 atomic nuclei, and this is the bond axis. Yeah, this is the molecular orbital, but no need to label this. Okay, this is the pi bond. Okay, this is the bond axis, and you can shade one of the loop, yeah, to show that about the position of the electrons at that particular time. Okay, so for example, in this shading area, the electrons will be located here. Okay, this is electron density. Okay, this is the bond axis. Okay, this is nuclei. Okay, so this is how we draw the sigma and pi bond. Okay, after we learn about what is sigma and pi bond, let's recall about hybridization. You already know that hybridization is the process of mixing atomic orbitals to produce the same energy hybrid orbitals. Okay, as you can see here, that if you want to make the hybridization, for example, in methane CH4, okay, First, we should make the ground state conditions of carbon atomic orbital. Okay, 6 electrons of C, 1s2, 2s2, and then 2p2. Okay, we draw according to energy level. Yeah, 1s is the lowest here, 2s, and then 2p. Okay, and you know that in methane there are 4 covalent bonds, single covalent bond. While in this ground state condition, carbon only has 2 single electrons. Okay, so not enough. So what carbon do is excited one of its electrons, yeah, from the lower energy level to the higher one, from 2s to 2p. Okay, we call this as excited process, yeah, excitation. So you can see after this excitation, there are 4 single electrons of carbon. Okay, we call this process as excitation. But once again, it cannot make overlapping orbitals since the energy of 2s differ from the energy of 2p. So what carbon do next is to make the hybridization process. There are several types of hybridization. First is sp3, and then sp2, and then sp. They differ only in how many orbitals that mix together. Okay, in sp3, there is one s orbital combined with 3 p orbitals. In sp2, one s with 2 p orbitals, and in sp, one s and one p combined together. Okay, so you can see that hybridization is like mix the 2 colors, yeah, mixing red and white paint, okay, to make the hybrid color pink. So this pink color has some properties of red color and some properties of white color, and it depends uh, on the color, on the part of the color. So if you have more red colors compared than the white, yeah, the pink color produced will be darker compared than if you have um, less red color. Okay, the pink would be lighter. Okay, so once again, in the hybrid orbitals, there are some properties of s orbital. There are some properties of p orbitals. It depends on how many orbitals that combine together. Okay, this is sp3 hybridization. 1s combined with 3 p orbitals to form, once again, that we call as sp3 hybrid orbitals. This is occur in methane. Okay, so 1s, you know that the shape is like this sphere, and then 3 p orbitals has the shape px, py, and then pz. They combine together to form a tetrahedral shape hybrid orbitals. Okay, this is carbon. Okay, and the bond angle is 109.5 tetrahedron. Later on, the s orbitals of hydrogen will overlap with this to make that we call a sigma bond between s orbital with sp3. Yeah, its loop consists of electron because this is overlap. This is the overlapping process. Yeah. So this is how we represent the sp3 hybridization. This is sp2. This is occur in ethene. Ethene is a molecule that have chemical formula CS2, right? C2S4. So you can see that there are 3 single covalent bonds. Yeah, 3 single covalent bond in one C. Yeah, for each C. But there is one more bond that known as pi bond. Okay, here. Yeah, to form double bond. So the pink is a sigma. So the excitation still need to occur since it needs 3 single covalent bonds. Okay, but the hybridization process only between 1s with 2 pi, yeah, to make the sp2 hybrid orbital, since once again it just need to make 3 single covalent bond, yeah, for each carbon. So this is sigma, this is sigma, this is sigma. Since only 3 sigma in 1C, so the hybridization is sp2. Okay, and you know that sp2 has a trigonal planar shape. Okay, like this. The bond angle is 120. Okay, imagine that there are two C's here. They overlap each other with trigonal planar shape. Okay, this is that means is a sigma bond, yeah, forms between hybrid orbital with hybrid orbital. Let me scroll this for you. Okay. This. So atomic orbitals overlap between hybrid and hybrid to form a sigma bond. Okay. This point. Hybrid orbital with hybrid orbital. Okay, let's continue. Then because in ethene there is a one pi bond, so we need to make this pi bond. Once again, you can see that through hybridization, there is one p orbitals that unhybridized, right? Okay, this one. Yeah, this is one hybridized p orbital. So let's draw it. I draw with orange color. Cause of one electron, and then they join together. Yeah, the process is like this. They will combine. Okay, like this. Nah, so you can see that electrons could be here. Okay, so in this case, the electron density at the above of the bond axis. Okay, this is the bond axis. You can also see that the loop at below of the bond axis also can combine like this. Okay, so this is the pi bond. Yeah, there are two loops below and above the bond axis, but electrons will be located at either side. It can be at above. Yeah, you can see this. That means this is where the electron density occur. But once again, at a particular time, the electron density could be moved, yeah, to the below. Yeah, when the electrons meet together at the below side of the pi orbitals.